So imagine you're at the edge of a cliff and you've got two cannonballs. One of them you're just going to drop straight down from the cliff. The other one you're going to launch from a cannon that's pointing straight out horizontally. Ignoring air resistance, if the two cannonballs get sent from the exact same height at the exact same time, one is dropped from a standstill and the other launched horizontally, which one will hit the ground first? Or might they hit the ground at the same time? I'll let you chew that over while we talk about projectile motion. And what projectile refers to is any object that's being acted upon only by the force of gravity. Gravity is the only force acting on that object. Because of this stipulation, we're just going to cancel air resistance for a bit. Let's ignore the effects of air resistance for now, so that we can get down to the nitty-gritty of what happens when an object is being acted upon by only gravity. Let's start with the simplest case of something that's just dropped. We call that free fall. We drop an object, say a lime. As soon as my hand stops touching the lime, the only force acting on it is the gravitational force due to Earth. Since there's nothing else acting on the lime, we know that this is a net force. It's an unbalanced force. And we know that if an unbalanced force acts on an object, the object is going to accelerate in the direction of the force, which is down toward Earth. We've learned from our discussion of gravity that the lime is going to accelerate at a certain rate. Again, you don't need to memorize this, but the rate is 9.8 meters per second squared. And just to make our lives easier, we're going to round that to 10 meters per second squared. What are those units? Meters per second squared, or meters per second per second. Remember the definition of acceleration, a change in velocity over a given time. This rate of acceleration means that the velocity of an object is going to change by 10 meters per second every second. So let's draw a little diagram to show what this looks like. This dot represents the lime's position at the exact moment we let go of it. We'll call this time 0 seconds, since it's the very start of the lime's journey. Here at time 0 seconds, the lime has literally just been released from rest, so its velocity is 0 meters per second at the moment. We let it go, and its velocity changes at a rate of 10 meters per second every second. This dot represents the lime 1 second later. It's fallen a little bit, and since 1 second has passed, its velocity has now changed by 10 meters per second. So at time 1 second, it has a velocity of 10 meters per second. Now, we'll pretend like we're dropping this lime. From a little bit higher. So what about at time 2 seconds? Its velocity will have changed by 10 meters per second. So that means it's now moving at 20 meters per second. And because it's moving faster and faster, remember, it's accelerating, it's covered more distance than it did in the first second of its motion. If we look at time 3 seconds, the lime now has a velocity of 30 meters per second, so it's covering even more distance in a given second. This pattern will continue. That's what acceleration is. It's velocity changing over a given time. And we saw that the velocity is changing at a constant rate, 10 meters per second every second. Thus, the acceleration is constant. The change in velocity is constant. Remember Newton's second law. Force equals mass times acceleration. If an object with some mass is experiencing a constant net force, it's going to experience a constant acceleration due to that net force. Constant net force implies constant acceleration. This is a big one. Lots of people think that in order to accelerate something at a constant rate, you need to apply increasing force. One place this stems from is the fact that in our everyday lives, where there are lots of resistive forces at play, you feel that you need to push harder and harder in order to keep something speeding up. Another issue is that lots of people mistake velocity and acceleration, and they think that the more force is acting on something, the faster it's going to go. But really, you can't tell the speed of something by knowing about the amount of force on it. You need more information to actually tell how fast something is going. You can't know by just the net force. For example, think about a sailboat. Say that you know that a big wind is pushing on the sail with a lot of force. Just knowing that, does that tell you how fast the sailboat is moving? Well, The wind might have only started pushing on the sail 2 seconds ago. The sailboat might not have been moving at all when the wind started. So even though there's a big force, the boat might not be moving more than a few miles per hour. Or maybe the wind has been blowing steadily for a while. The sailboat may be zipping along at 30, 40 miles per hour and speeding up still. What I'm getting at is it's like a logic problem. If the only piece of information you're given is that a net force is acting on the boat, and you're asked how fast the boat is moving, the correct answer is there's not enough information. But you could tell that the boat is accelerating. If it's a strong wind, the boat is accelerating a lot. If it's a weak wind, the boat is accelerating a little. In fact, if you know the strength of the net force and the mass of the boat, you could use Newton's second law, force equals mass times acceleration, to calculate exactly the boat's acceleration. Now, we won't do all that in this course, but what I'm getting at is that force and acceleration go together. Knowing about net force allows us to know about acceleration, but not necessarily velocity. So, a lot of times we confuse the relationship between force and acceleration for velocity. One other manifestation of this is a particular idea about gravity for an object in free fall. Remember the lime we dropped? As it falls, it's moving faster and faster. Some people might see that and say, the lime speeds up as it falls, so that means that the force of gravity must be increasing, or the force of gravity acting on the lime gets stronger and stronger the more the lime falls. We can debunk this in a few ways. First, you might remember that gravity doesn't change all that much over such a short distance. You have to get miles and miles above the surface of Earth before gravity actually changes by a noticeable amount. So, we consider the effects of Earth's gravity as constant, anywhere that a human might reasonably be, whether that's on the surface of Earth, in a skyscraper, or even in an airplane. So the gravitational force acting on a lime we drop by a few feet is going to be constant. Further, we know that an object that's speeding up at a constant rate is simply being acted upon by a constant force. For the lime, that's the force of gravity. So we've explained the motion of an object that's simply dropped. But what if instead of dropping a lime, we throw it straight upwards? I use my hand to exert force on the lime in order to throw it, in order to get it to start moving upwards. And as soon as my hand lets go, what forces are acting on the lime? What is interacting with the lime at the moment? Well, we know we're ignoring air resistance. So besides that, the lime is just interacting gravitationally with Earth. There's the downward force of Earth's gravity acting on the lime, and nothing else. My hand isn't touching the lime, so I can't possibly be exerting force on it still. My hand and the lime are no longer interacting once it's left my hand. The net force on the lime is just the force of gravity, and we know that a net force means acceleration. So the lime must be accelerating downwards. But we know that right when I let go of the lime, it's moving upwards. So what does it look like when acceleration and velocity are pointing in opposite directions? Well, we might remember that if an object is slowing down in a straight line, there must be a net force in the direction opposite to its motion. And that's what we see, right? After I throw the lime up at some initial speed, it starts moving slower and slower. It's slowing down in a straight line because its motion is the direction totally opposite to the direction of the gravitational force acting on it. Now, because the lime is continuously slowing down, at a certain point it's going to have a speed of 0. That's what happens to the lime as it reaches its peak position. It reaches a certain height at which it won't keep moving upwards. When the lime is at the very top of its path, for a moment, just a moment, its speed is 0. But it's still being acted upon by gravity, of course, and so it continues to accelerate downward, but this time it's moving in the same direction as the net force. And what happens when a net force acts on an object in the direction of its motion? It speeds up. Basically, we'll see the same thing happen as if we were to have dropped the lime from its peak position. Now, there are a few other ideas that people might have to explain this. Just like how some believe that the force of gravity builds up when the lime is falling down at faster speeds, some believe that the force of my hand continued to act on the lime even after I threw it. But how could this be possible? Remember that a force is essentially an interaction, And the way my hand interacts with the lime is by touching and throwing it. Once I've let go, though, how could my hand still be acting on the lime? Well, a common belief in intro physics students is that force is something that can be stored inside an object, like a car stores fuel to use when it needs. Some would say that even after I've let go of the lime still has some force from my hand inside it somehow, and that force dies out gradually until the lime happens to be overcome by the force of gravity. This type of belief was actually the norm a few hundred years ago, until people like Galileo and Newton came around and happened to have better, more complete theories. Basically, to avoid this thought trap, we should just remember that a force is an interaction. And there are few types of forces that allow for interaction at a distance. That's gravity and electric and magnetic forces. That's it. All other forces are contact forces, meaning they require contact. Things like friction, tension, air resistance, or even a simple push from your hand. They all need contact in order to happen. And they happen immediately. There's no delay. No building up or wearing out. A force is simply a force, and it acts on the object in its entirety for as long as the force is applied. Now, let's return to our thought experiment from the beginning of this video. You're on a cliff, and you have two cannonballs. One gets dropped from rest from the edge of the cliff, and the other gets launched horizontally. We've just seen what happens when you just drop an object, so let's think about the cannonball that gets launched. Say we're looking at the cannonball the moment it's left the cannon. It has some speed, right, because it's been shot. So it has a velocity that points to the right. And we know that the only force acting on it right now is gravity. So the cannonball is initially moving to the right and accelerating down. From our previous observations of the way things move when we throw or launch them, we expect that it's going to follow a path that looks like this. Some might wonder, if it's only accelerating down, then why doesn't it just fall straight down? And to that I could ask, where's the force to stop it from moving to the right? The net force acting on the cannonball simply points down. There's no force pointing to the left to resist the rightward motion. Now, in real life, there would be some air resistance, but not nearly enough to stop a cannonball in its tracks. We know that the cannonball realistically will end up following a path that looks like this. The net force on the cannonball points down. The force of gravity has nothing to do with the left or right motion of the ball, but it has everything to do with its downward motion. Remember how we're able to split up contributions that act at right angles, like how northeast is a little north and a little east? The same kind of thing applies here. Without the effects of air resistance, the ball is going to continue moving to the right with the same speed in that direction. Imagine if there were no gravity. The ball would just keep moving to the right forever because there would be no net force acting on it. But because there is gravity, the cannonball is also going to start moving down. These two things, moving right and moving down, function independent of each other, but together they result in a motion of the cannonball that's to the right and down. Let's focus on the down part for a moment. At time 0 seconds, right when the ball has left the cannon, it's only moving to the right, so its downward velocity is 0. But 1 second later, the downward velocity will have increased by 10 meters per second. 1 more second later, it will have increased by 10 meters per second again. So now its downward velocity is 20 meters per second. See where I'm going with this? The downward motion of the cannonball is simply due to gravity. The ball started with no downward velocity, but then it increased by 10 meters per second every second. This downward motion functions the same as if we were to have just dropped the ball straight off the cliff like the other one. Therefore, both cannonballs move downward at the same rate. This makes sense because they're both being acted upon by the same force in the same direction. They both accelerate downward at a rate of 10 meters per second squared. So, which one will hit the ground first? They're both going to hit the ground at the same time, although this cannonball is going to land much farther away from the cliff since it had some rightward velocity that entire time. So, to summarize, in this lesson we've learned that a projectile is an object that's only being acted upon by the force of gravity, and therefore will accelerate downward at a rate of 10 meters per second. Because only gravity is acting on a projectile, we ignore air resistance to talk about them. But in real life, air resistance doesn't really change their motions all that much from what we see when we take this theoretical no air resistance view. We've stressed the fact that a constant net force implies constant acceleration, or a constant change in velocity. We have to be careful not to confuse velocity with acceleration. For instance, we can't tell the velocity or speed of something that's moving just by knowing about the forces acting on it, but we can tell about its acceleration. We saw that when we throw an object, the force from our hand stops acting on the object the moment we stop touching it. And with this, we talked about the misconception that an object can store force inside of it somehow, which isn't really how it works. Force doesn't build up or die out within an object. It's either acting on it or it's not. And we saw that the up-down motion of an object is independent of its left-right motion. So even an object that's launched or thrown sideways will accelerate downward at the same rate as an object that's only traveling downward. Okay, this is it, y'all. Instruction is over. I hope you've learned something useful. Hope it was interesting. Thank you so much for sticking with me here. Your support means the world to me. You know what's the greatest force of all? Love. And it can act by contact or at a distance.